right, and this is more whole right. So 50% should exist here. But there is no state in the gap at Fermi energy equals 0. So the Koji particle in the superconductor cannot be Majorana zero mode. Yeah, zero mode. Oh, sorry. Zero mode means energy 0. That should exist here. And actually, the Koji particle in superconductor is expressed by the Bourdieu particle, the superposition of electron hole, and also the electron has spin. This is also another problem to realize Majorana. That doesn't have spin. Okay, the series is complicated for me. So how to realize it in the with the familiar materials for us. So this is one suggestion, proposal to realize Majorana zero mode in semiconductor nanowires. So semiconductor nanowire with like indium arsenide or indium antimonide, which have the large spin-orbit interaction. And this nanowire is put on the superconductor, S-wave superconductor, ordinary one, like aluminum or niobium, then induce superconductivity into the nanowire, then apply magnetic field to destroy time reversal symmetry. Then the Majorana zero mode should appear at the edge of the nanowires, this nanowires. So nanowire has to be one-dimensional, ideally, but in reality, it's not easy. So they're looking at the energy band in this 1D channel. So because of this large spin-orbit interaction, this spin-up band and spin-down band are separated by the spin-orbit interaction. Then by applying the magnetic field, you induce the Zeeman splitting here. Then you see two bands, this band and this band. And you tune the chemical potential inside this gap, Zeeman gap. So then you have the single band. The spin degeneracy is lifted. Then if you induce superconductivity between this electron and this electron to form the Cooper pair, this is a prescription to realize Majoranas. So depending on the chemical potential and magnetic field, in this region, shown by green, it is a topological regime where then the Majorana zero mode should appear, and the other areas, regions, it's a trivial area, not interesting. So this is from this paper. It's a very interesting and review paper. And this this scheme was predicted by the theory papers, this theory paper. And then followed by the theory, the Delft group reported the really first experiment, a very interesting experiment. So idea is that they have indium antimonide nanowires and touched with the superconductor, I think aluminum in this case. And this side is just a normal metal. So then Majorana should appear here and here, touched with superconductor. If there is Majorana zero mode at the edge of the nanowire, the superconducting part, they can measure this Majorana zero mode by measuring the current through this Majorana zero mode. And actually, you see there are many gates to form the quantum dot to do the spectroscopy. And they found, what they found was this. So as this is differential conductance as a function of voltage, and you see as a magnetic field, this is basically the superconducting gap and of aluminum induced in the antimonide. So you see as you apply magnetic field, some new peak appears. So this seems to be, this is called a zero bias anomaly, seems to be suggesting the existing of Majorana zero mode. So other group also observed the similar effect of zero bias anomaly, but it is not confirmed whether that this peak is coming from Majorana or not. Maybe not. So there are still arguments on this. So another possibility is to use the helical, one-dimensional helical states, this formed in the two-dimensional topological insulators with some magnetic field. So topological insulators, two-dimensional topological insulators are experimentally confirmed, demonstrated in the transport measurement in the mercury telluride or monolayer tungsten ditelluride. And there are other proposals to realize the two-dimensional topological insulators. So in the 2D TI, if you think that this 2D TI, the bulk of the material is insulating with energy gap, and the edge, along the edge, there is a metallic state, one-dimensional metallic state, and there is a momentum spin rocking, meaning this direction, moving this direction, electron have upspin, and opposite direction have downspin. Then, so this is the situation of this Dirac, kind of Dirac cone along the edge. Then you apply the magnetic field to open the Zeeman gap to destroy the time reversal symmetry as in the case of semiconductor nanowires. Then you induce a Cooper pair, introduce a Cooper pair between these two electrons. So then the edge itself would be Majorana channel, so-called Majorana channel. But in this case, there is no end, so maybe Majorana is extending. So in this case, this is again the mapping, so topological regime and trivial regime as a function of chemical potential and magnetic field. So yeah, this prediction was made earlier than the semiconductor one, in this seminal papers. So yeah, we want to somehow